I'm working on sort of a new layer on top of Racket's existing macro system called syntax spec. And I call it a new style of macro system, a multi-language oriented one. And I'll go into what that means. At the beginning, I just want to call out that this is joint work with lots of collaborators who've helped me make it real. So call out to Matthias, Jason, Mike, Mitch, Alexis, and Sid, among others. So this is, to begin with, I want to talk about sort of the style of programming that Racket already enables somewhat, and that syntax spec is aiming to enable even better. And that is what we call language-oriented programming. So solving a programming problem by using multiple domain-specific languages together, together with sort of general purpose code. So this is an example of a program written in this language-oriented style. It uses a combination of Racket and two different DSLs, the Rash shell scripting DSL embedded in Racket, and the pattern matching language in Racket, which, though it's sort of familiar to everybody, it's part of Racket, it's really a DSL that's sort of built on top of Racket and provided in the core library. So sort of we've got the different fragments of code in the different colors here. And the task of this program is to perform this transformation on a directory and subdirectories full of JSON files. So every file in this directory, these subdirectories, is all in this format where it has this results field, and there's always exactly one result. And we'd like to transform those JSON files into files that just have that result in it. So there's a number of sort of different tasks that we have to accomplish. We have to search the file system for these files. For each file, we have to sort of apply some transformation on it. We have to read the JSON file. We have to write the JSON file. We have to do the pattern matching. So we're going to accomplish those pieces using these different DSLs. We're going to use Rash to interact with the Unix shell so that we can use the find command in the Unix shell to search for all these files. And then we're going to use this each line pipe. So this is sort of a pipe that intermediates between the Unix shell and Racket. We're piping each line not to another shell command, but to a Racket function, to the fix file Racket function. So that's in red. And the fix file function is going to use Racket code to read the JSON file and write the JSON file just using the JSON library in Racket. And then since we have this pattern matching task, we're going to use a match DSL to say, well, this is what the JSON structure always looks like. We've got this object with results and a list. We want to pull that apart and just return V. And otherwise, if it doesn't look like that, we're just not going to transform it. So in this program, we're not actually only using DSLs. We're actually also going even a little bit further, and we're using extensions to DSLs. So the core match DSL doesn't know anything about JSON. It doesn't give us this nice patterns with sort of different kinds of braces for objects versus lists. But we can very easily write a match expander that extends match to add this special syntax for JSON. And we might do that if we're doing lots of pattern matching on JSON structures. And similarly, the Rash DSL doesn't have this each line construct built in. It has some sort of lower level constructs for dealing with streams of data. But we can, as a macro, add on a new kind of pipeline operator to Rash and extend it. So this is the style of programming that I think is very cool that you can do in Racket sort of somewhat uniquely, and that I would like to make even better. But it isn't just Racket. So ideas from Racket's macro system have made it out into the world. Rust has adopted some of the ideas. So this is a very cool DSL in Rust called Ascent. It's an embedding of data log, so a logic programming language that sort of does bottom-up search and sort of database queries. And this particular program uses a mixture of sort of Ascent data log code and Rust code. And you can combine those sort of very fluidly. And so the sort of applications that Ascent was created for was to do things like accelerate large-scale static analyses using data log to do some part of that. And so one thing that the Ascent developers really care about is being able to compile this Ascent code into really fast Rust code that interacts with your Rust data structures really efficiently. So the Ascent macro here is actually a full optimizing compiler for data log. that is generating efficient Rust code. So this is sort of another dimension of language-oriented programming. We don't just want to provide lots of different high-level syntaxes. We also want to be able to provide optimizing compilation or other custom things like maybe a type system for our DSL. That's sort of another goal. So the subject that I'm talking about today are sort of what are the tools that are going to let us accomplish this kind of language-oriented programming, going to let us make DSLs like this. And my claim is that macros work, and we've gotten a long way on the kind of macro system that we have in Racket. But they were really designed for sort of a different task. They weren't designed originally for making DSLs. They were designed, in my view, more for the task of creating syntactic sugar, a big language on top of a small core, that sort of lambda the ultimate idea from Guy Steele and Jerry Sussman, those papers where everything can elaborate down to lambda and you can have a compiler for lambda. And macros are a really great enabling technology for that. All of the syntax that we use in Racket today compiles down to this very small core, or expands down to this small core that then gets compiled. But what would it look like if we thought about the desiderata specifically for making these more sophisticated DSLs that are sort of more different from Racket, and designed a macro system around that objective from the beginning? What would we do differently? So to get there, for anybody in the audience who's not already super familiar with Racket's macros, I'm going to start with a little introduction on how those look and some sort of salient points for these issues. We're going to look at what happens when we try and build a DSL with conventional macros, and sort of what goes wrong in my view. And then this sort of new kind of macro system and this particular implementation of it, syntax spec and Racket. And then I'll show you some of the cool DSLs that we've built with various collaborators. And hopefully at the end, you will be chomping at the bit to build your own. So, all right. So starting with what conventional macros look like. So this is a Racket module, and we are defining a new piece of syntax, and then sort of immediately using that new syntax that we've defined at the bottom, and also exporting it from the module system. So the first sort of point here is that macros are very deeply integrated with Racket and its module system. You can define them and use them immediately. You can provide them from modules. And what this syntax is it's just a nicer syntax for using the map higher order function. The real for list in Racket is much fancier. But this particular macro is just translating into map. So the way that translation works in Racket to define a macro is we define a function that takes syntax objects and produces syntax objects. So those are things that are effectively S expressions with a bunch of extra data attached to them. And that's at essence what a macro is. But here we're able to use patterns and templates to do that transformation because we're using the syntax parse meta language to implement that transformer. But we could, in principle, use sort of arbitrary Racket code at compile time to do that. So you can see that we're importing require for syntax parse to be able to use that meta language. So that's how we define macros. And a salient point that I want to mention is that we didn't have to say anything about the binding structure of our new syntactic form that we're creating. So we're creating a form that has this binding structure where it binds x to each element in the list in turn as we iterate, right? And we didn't say anything about that, and yet our IDE understands how that works. And also, the macro expander understands enough about the binding structure in order to provide us what's called macro hygiene, which is making sure that, for example, our reference to the map function is sort of reliably refers to the map from core Racket, even if this macro were to be expanded in a context where map meant something else. So the important point here is that both the macro expander and the IDE are understanding some important things about the structure of the syntax that we define, sort of based on how we expand it. So this tight sort of integration with Racket and the macro expander's understanding of Racket makes this kind of macro definition really easy in a lot of ways. We can reuse the module system to sort of control what parts of our DSL get exported. We can reuse the binding structure, again, by expanding to Lambda. We get the ID services for free. And we also get the fact that sort of different extensions work together properly, right? Because every extension is just extending the language of Racket expressions and expecting Racket expressions as sub-expressions. then it's, we can trivially use different extensions to the language together. So all of this is really a great approach for accomplishing this sort of lambda, the ultimate goal of having syntactic sugar over a small core language that the expander really understands well, and being able to build a bigger, more sugary surface language on top. But then I think the question is, what happens when we start building more complex domain-specific languages using this same technique, which is what we in Racket are now trying to do? And in order to be able to talk about that, I have to introduce you to a particular domain-specific language. This is just one that I work with a lot, so I'm going to choose that. So it's the Minikenran logic programming language. And for the purposes of this talk, all you have to know about Minikenran is that it is sort of logical statements, logical connectives on top of a primitive equality constraint over tree data. So equal is gonna take two terms which are things that look like S expression data and say there must be an equality between this. And then we have some other sort of connectives. We can disjoin two logical statements, conjoin, or do an existential binding with fresh. So the program on the right is a predicate that holds true when its argument is basically something that looks like a piano numeral but expressed as a list structure. So we can see when we query that with run on the bottom that the first three things that look like lists representing piano numerals are z, s of z, and s of z. And the way that we defined this is sort of as this recursive logical formula. So there's two cases. The first is an equality constraint that the number must be the symbol z. And then the second option is the number is a list whose first element is the symbol s, and the rest of that list is also a piano numeral itself. So that's sort of how we're defining this predicate. So that's just a small program. And not only do we want sort of Minikenran code on its own, we also want to be able to create a DSL where we can mix Minikenran code with Racket code in interesting ways. So here's a particular program where we really have a motivation to do that. It's defining a relation called route that relates two places that you can get to by taking plane flights. And the direct flight relation is where you can get to by taking a single plane flight. So the route relation is going to be the sort of transitive closure of the direct flight relation. And the route relation is very pleasant to implement as sort of a recursive logical formula in Minikenran code. But the direct flight relation, if we were to write plain Minikenran code for that, would be a disjunction with thousands and thousands of equalities, constraints. So that's not what we want to do, obviously. We want to look up real data from a real database that's up to the minute and accurate. So that's where we want to escape out from our DSL and use some Racket code instead. So the Racket code's in red, and it's just using Racket's database library to access the database. And the forms in black here are sort of the boundary forms that are going to mediate this interaction. So we have a Racket module, and inside that Racket module, we have the def rel boundary that says, OK, now we're going into Minikenran code. Or if we're in Minikenran code in a relation definition like direct flight, we have the boundary form goal from expression that says, let's go back into Racket code to compute this particular part of the goal. So that's the language that I want to think about. And then I want to say, what are the properties that we would really want to have in an implementation of Minikenran or any other DSL, right? So some things that are important are for us to be able to get the domain-specific advantage of the DSL, whatever that is. It might be syntax, it might be the static semantics. It might be that we can make a really good optimizing compiler for the DSL because there's some sort of domain-specific structure that we can take advantage of, right? And these are all things where the DSL is going to be different from Racket in an important way. So it's important that we would be able to sort of create that distinction from Racket and do something different and somewhat unique from Racket in order to get our domain-specific advantage, right? But at the same time, we want it to be easy to integrate with Racket and with other DSLs in the way that we saw on that first slide, right? So we want to be able to interact with Racket, but also because of those differences, we have to make sure that that interaction is safe, right? We may be doing optimizations in our DSL, and we want to make sure that the way that we interact with Racket doesn't sort of break that. And other forms of integration that we want, well, it would be nice if our DSL was macro extensible. Again, just like we saw on the first slide, being able to add those extensions. And we'd like to be able to have good IDE services, just like we saw that we get for the syntactic sugar. So those are things that we might want. And let's look at what happens when we try defining DSLs using the current tools that we have in Racket. So one approach that we can take is what I call macro embedding, which is where we're going to define a bunch of individual macros for each syntactic form in the DSL. So I have to define a macro for defrel, and also one for fresh and disjunction and conjunction and equal. Every syntactic form is going to have its own macro. And they're both just going to translate to some Racket code that implements the behavior we want. So in this case, we're saying that relation definitions we're going to implement using Racket procedure definitions with define. And then our expansion process, if you looked at this in the Racket macro stepper, you would see that each of these macros is going to sort of expand separately. So the first step is expanding that defrel to define. But then we are going to expand the disjunction form, and then the fresh form, and you can sort of see the code going from minikenron to Racket based on that color change as we go through that expansion process. So this approach has lots of benefits. The integration with Racket parts work really well. But the big flaw is that no macro is looking at the entire DSL syntax, and we can't implement an optimizing compiler or even a type checker or other things like that, right? We're not getting our domain-specific advantage that was so key to our objective of making a DSL. So this approach has that flaw. We could take a different approach, which is to say, well, instead of writing lots of little macros for the individual syntactic forms, let's write one really big macro, which will sort of be the optimizing compiler for the entire DSL. And that's what happened with Ascent, that Rust language that I talked about earlier. And we could also do that for minikenron. And so within this macro, we'd go through sort of conventional compiler passes. We'd have a parser, we'd have a type checker, we'd have an optimizer, we'd have a code generator. And it's going to operate, in this case, sort of over one big chunk of the language over an entire relation definition. And so we can optimize within that relation definition at least, right? So this is an approach that will get us sort of our ability to do custom things because we control that syntax, right? But there are some other consequences on the other side. So let's look at those. So this is what they did for Ascent, and so we can look at some of the consequences of doing that for Ascent in Rust, and what happens in Racket is quite similar. So here I'm trying to use IDE services for this Ascent language. And so I'm hovering over Node here in VS Code with the Rust Analyzer extension. And what I would hope it would tell me is that, OK, well, Node is a relation that you defined up there, and maybe something about the type of the node relation, things like that. And what I, in fact, see is something about for each loops and iterators, right? Which is not anything that's in the surface syntax of the DSL at all, right? And the reason why I'm seeing this is because, well, I wanted that efficient compilation. This is the code that it compiles to, right, to efficiently implement my query. And that's all the IDE has to work with in terms of what it can show me things about, right? And that optimizing compilation has created some sort of semantic distance between the surface syntax and the generated code. Another problem here is that because the Ascent macro is taking control over this entire fragment of syntax, it's not macro extensible. Or at least it's not macro extensible thanks to the host macro expander. They wrote their own macro expander in their big optimizing compiler in order to make it extensible. And that's a thing people have had to do in Racket a bunch too, right? There's a custom macro expander for match and for syntax parse and a bunch of other languages in Racket, right? So that's another big drawback of the one big macro approach. And then finally, another big challenge here is the interaction between our DSL code and Racket code and the way that interaction is sort of mediated. If we write one big macro, the way it's mediated is in terms of whatever we compile to, right? And so we have to sort of be careful about what we compile to. So here's a particular example of that. We have a relation definition. The first thing we do is this equality constraint, x is the pair cons 5, 6. And so according to sort of minikenron's semantics, the declarative model that we expect, x must inevitably be 5, 6 forevermore, right? It's sort of a monotonic logic programming language. And so when we get down to the line equal yx, we should still be able to be sure that x is still 5, 6, and therefore y should be able to be 5, 6. Our compiler ideally would be able to sort of inline or constant propagate the value or perform other optimizations relying on that monotonic semantics. But in fact, depending on how we compile to Racket, it may be that Racket code could sort of expose the internal data structures of our implementation. So if we want a fast implementation of miniKanren, we sort of want to compile the procedure argument x to be just a binding with whatever the internal value is. And if that value is a logic variable, well, logic variables in miniKanren happen to be implemented by mutable vectors. And so we can sort of reach down into the implementation and say, well, I'm going to change the field in that vector that sometimes contains the value of this variable. And if our Racket code does that, then whatever our compiler thought was true just isn't true anymore, right? And our optimization was unsound. So to protect ourselves from this, it starts getting a lot of work to protect yourself from this. You can kind of do it, but that's another big issue, and that's where sort of this multi-language structure really comes in. So we can solve all these problems in Racket because Matthew and others have gone to a great deal of effort to create the syntax local API. And so if you learn about these 45 functions, you can become a Racket macro expert, and you can tell the Racket macro system about the structure of your DSL syntax that you've taken responsibility for in your one big macro. And you can make it expand macros inside that. And this is something that I also worked on to make it easier for people to write their own custom macro expanders using sort of a layer on top of this API, right? But ultimately, my conclusion is that you need a PhD from Northeastern or from Utah to really, really effectively use this system. And so if we want to build something that everybody in this room can use, hopefully, to build sophisticated DSLs, then we sort of need another approach to solving this part of the problem. So here's the problem. Right now, we can't get everything that we want, easily at least, without a PhD. So the next question is, yeah, what would we do differently? How would we design differently in order to solve this problem? So that's what I'm trying to do with syntax spec, this new layer on top of Racket. So the first design decision is to assume that we're going to want to get that domain-specific advantage of optimizing compilation, and therefore that we're going to want to compile in sort of this whole fragment way. We're going to want to do something like the one big macro approach. That's sort of the first design assumption. But then the second piece is that we're not happy with this sort of syntax local API. We need some way that is much, much easier to specify information about the syntactic structure of that DSL fragment so that the Racket macro expander can integrate with it. So this is where I bring in sort of the meta languages that you have in language workbenches like spoofx, where you can specify sort of more syntactic structure than we can today in syntax parse. You can specify sort of the grammar for an entire language, and also things like binding structure that are necessary to sort of mediate this interaction. So that's the second big idea. And then the third big idea here is that we want to think about the way that our DSL and Racket are going to interact. And we can take some ideas from multi-language semantics to make that interaction a little bit more explicit and protected, so that we can have our optimizing compiler, but also have some safety. So let me show you what that looks like. So here's what a specification looks like. And three essential parts: grammar. So we're going to say, well, we have goals. Those are different than expressions. We have goals that are different from expressions. There would also be terms. We're going to say something about the binding structure. So we're going to say that fresh creates a scope, binds a name, and that the body is in that scope. And this is going to let us implement sort of macro hygiene for free, extensibility for free. And it's also going to help us mediate the interaction between languages in terms of shared variables. And then finally, we're going to make explicit the connection to Racket. So we're going to define these boundary forms like goal from expression and say, well, this is where a Racket expression is allowed and nowhere else, right? And then finally, sort of the host interface form are our entry point to the DSL from Racket. So it's the other side of that boundary. We're saying a relation definition sits in a racket definition context, and we're going into the DSL there. So that's what a declaration looks like. And I just want to tell you some of the benefits that we're going to get from that, what it looks like. So one is if we want to do this domain-specific optimizing compilation. So an example is we want to do a partial deduction here, where we say, well, we know these two equality constraints can really be simplified because we don't use x anywhere else. So we can infer that y must be 1, z must be 2. And let's just simplify our logical formula to that as part of our DSL compilation. And that's going to work because in this system, after sort of the parsing and macro expansion process managed by syntax spec, we're going to come in and we're going to get the complete DSL syntax. And so we can do that sort of one big macro approach here, except that the syntactic structure is already understood. So we don't have to parse it. We already, and we can query, ask syntax spec questions about the structure of that syntax, about binding structure, things like that. So sort of the front end of our compiler has already been handled for us. The second part that we might want is, well, can we build extensions? So we might want to be able to build a pattern matching extension on top of minicanron, where we say, instead of writing these low-level logical formulas, let's write something that looks more like functional pattern matching code. And we want to write that as a macro. And with syntax spec, we can do that by writing fairly conventional syntax parse macros. There's only a small difference here that we say define DSL syntax instead of define syntax. And we say what kind of macro it is. So this is a macro that extends the context of minicanron goals, logical formulas, as opposed to something that extends racket expressions. And then the way these sort of two things interact is that syntax spec manages the expansion of all of the DSL macros down to the core DSL language that you specified in syntax spec first. That's the first step. And then the second step is that sort of that whole fragment compiles together with the sort of one big macro approach for the compilation afterwards. And so I just want to point out that this is exactly the structure that Racket itself is implemented with, right? We have an extensible front end with macro expander, optimizing compiler for a fixed set of syntactic forms as a back end. And we're just lifting that idea up to say we should be able to build DSLs that have that same structure. I think I am running short on time. I will just say that also having that multi-language structure and the binding information means that the macro system can help us automatically insert sort of boundaries and contracts between the language. So here it can see that we have a reference in Racket code to a logic variable that was bound in DSL code. And it can say, well, in that particular case, when you have this cross-language reference, let me insert something. And that thing that we're going to insert is going to result in a contract violation in this case. So we can protect those boundaries. So you can see how we sort of get all of these things that we wanted together via this mediation of having an understanding of our DSL core syntax in the middle. And it turns out I don't have time to talk about them today, but each of these things sort of mutually supports each other. So we get some benefits that it's easier to write extensions when we can assume that there's an optimizing compiler working on the generated code from our extension after the fact. I have an ICFP paper about this if you'd like to read it, but I can't tell you about that today. For people who are used to creating DSLs in Racket and trying to make their IDE services work when they have a sophisticated compiler, you might know that you have to do some special things like sprinkle these disappeared use properties on the code that you generate to say, well, this got optimized away, but I'd like the IDE to know about it. And in syntax spec, because we've told the macro system about the surface syntax of our DSL, it can make those IDE services work without sort of this magic. So we've built lots of DSLs in syntax spec. In addition to the minicanron implementation, there's another one. Chi also has an optimizing compiler now, thanks to syntax spec, that does some deforestation. And we've built just a bunch of other DSLs that are all rather easier to build thanks to the syntax spec language. So overall, sort of the benefit here is that we've got this learning curve. You start by learning how to do syntax rules, these little syntactic sugar macros. You might learn how to make macro-embedded DSLs, which are sort of great for prototyping. but I can't do an analysis or a optimization. And then, the story in Racket so far was that when you wanted to step up to that much more sophisticated DSL, it was a really big jump, right? And we've got a new sort of point on this learning curve where with syntax spec, it's not so big of a jump. And you lose a little bit of expressive power, maybe. So there will still be benefit in being a true Racket macro system expert. But we've sort of filled that gap. So yeah, this is the promise. You can get it all without a PhD in macrology. And it's out. There's documentation. So give it a try. Thanks.
All right, maybe time for 1 or 2 questions. Do you want to? No.
Charles, not from any university. Is this something where you could define a DSL in terms of another DSL and have multiple layers before you get to Racket?
Yeah, so you can certainly have the compilation target another DSL. When there are currently some limitations about sort of I guess the compilation has to target Racket, but it can be Racket including other DSLs, right? So there are some trickier issues on how to make the meta language work where such that you can say, well, this is really an extension to a DSL, but a syntax spec defined extension to that other DSL. Not all of that works right now. You kind of have to go through Racket at some points, but you can usually paper over those interactions with additional macros sort of covering up the interaction.
This is great. I'm Ashton Wiersdorf from the University of Utah. This is great, and this seems like something I really want to use. Is there any hope for other languages besides Racket?
Absolutely.
What did you built syntax spec in Racket, right? Yeah. So if I'm say I don't know, Elixir or Julia,
Rust, right?
what do I need? Or Rust? Yeah. Is there any hope for me?
Absolutely. So if you're Rust, what you need to do is hire me to go build the equivalent of syntax spec on top of Rust. But is layered on top of a procedural macro system, right? It is a macro-defined macro itself, syntax spec is. So if you have a procedural macro system capable of doing macro-defining macros, like Rust has, then we can build something like syntax spec on top of Rust as well. Now, then the question is the power of the reflective API is going to control how much we can integrate a syntax spec-defined DSL with Rust code. And that would probably need to be extended, but definitely the idea is something, it's designed so that we can bring it to other languages.
Oh. How are we on time? Do you think we can take a couple more? Okay. All right, Jacqueline.
Hi, I'm Jacqueline. I also commit macro crimes. Are there any DSLs in Racket's main distribution that you think this would help improve the implementation of or add new features to?
I think that sort of the DSLs that we've created in the main distribution and tried to make macro extensible have been, we've done ones where we could handle it okay. Like Match is a macro extensible DSL like this, but it doesn't have a lot of sort of internal binding structure. It only has sort of one layer of binding structure, and that's not too painful with what we have now. So I don't have good examples of things that we've done. I think this is more about pushing the boundaries of things that we could do. I guess contracts. Contracts could be improved, and a contract optimizer. I saw Robbie waving his hand, so. Oh yeah, Redx would be great.
But it is.
Yeah.
All right, we have 2 other people with hands. How are we doing on time? What time is it? Okay, well, we do have a slightly longer lunch break, so we'll just take these 2 questions, and that will be the end. See you.
Yeah. William Bowman from University of British Columbia. So I'm wondering about, so you gave an example like mini Canron, and you can define all the core forms in syntax spec, but I'm wondering about if you want those core forms to be extensible themselves. So I want to add a new extension to minicanron, a new core form. Is that possible with syntax spec?
So that's a design decision that I made was to assume that the core syntactic forms of your language are going to be fixed. I think that makes a whole lot of things a lot easier than trying to have an extensible target language. And I think there's also sort of cultural benefits of, if you have somebody working on an optimizing compiler, if you have to assume that other people are going to be plugging in other stuff, it's kind of hard to make the right assumptions you need. And there's sort of a community process that I think has to happen of, we really want more capacity here. How do we work together to figure out how to design the compiler around that? Now, what you can do is you can take advantage of the fact that you can escape to Racket. And depending on how you've designed that interaction with Racket, it may be possible to define extensions that wouldn't be expressible in minicanron themselves, but are expressible in the multi-language combining minicanron and Racket. So for example, I can make a database query extension that looks native to minicanron, which I couldn't do just by expanding to minicanron, but I can do by expanding to the multi-language.
All right, time for one question.
Hi, I'm Ben. I'm not affiliated with the university, so hello. Since this is our last question before lunch, I'll finish Ashton's question and ask what's on everybody's mind. Do we have enough pieces to build Hashlang Rust now?
Well, okay, so an example of, where I got to this was from type systems as macros, and Alexis tried to build Hackett, right, which is something like that. And I think if you wanted to make a macro extensible Rust, which you probably want, right, ideally you'd have like the type system of Rust and macros sort of interacting in interesting ways. And syntax spec right now is not quite powerful enough to do that, but the extensions we've made to the procedural API under the hood make it easier to make sort of new macro expansion protocols. So if you tried to do something like Hackett again today, I think it would be much easier to do well. I'll say that.
All right, I think we'll break for lunch, and we'll see everyone back here. Yeah, let's give it up for Michael again.